It's a pleasure to welcome Philippe LeFloch, who will talk about on the scattering laws of bouncing universes. Please.
Thank you very much for this invitation. And let me first say that this is a joint work with Bruno LeFloch, he's in Paris, and Gabriel Veneziano in Geneva. And what all of that will be about are recent developments on the Einstein equations, especially on self-gravitating matter. So I'm interested, as you will see, in most of my work in the past 15 years was to analyze matter with self-gravitation taken into account. And especially in this talk, what I have in mind are waves, shock waves, or phase transition interfaces together with gravitational waves. Right, so you have all this setup. Of course, if you take all these effects into account, it would be extremely general and very hard to do any advances, mathematical advances. So you have to somehow formulate the right questions. I show that in the next slide. And basically, the tools I have, the techniques I have in mind are techniques of Lorentzian geometry, especially with metrics having low regularity or weak regularity, because I have this in the idea to cover interfaces, singular interfaces. And even more specifically, you will see that the spacetimes I'm talking about have singularity hypersurfaces, where, say, the curvature blows up or other physical quantities or geometric quantities blow up. So the techniques involve Lorentzian geometry, PDEs, and some physical modeling. Eventually modified gravity should come in the picture, but you will see that at the level we are, it's elementary to some extent. So what we want to do here is to propose a perspective, a mathematical perspective on bouncing cosmologies. And this is an old problem. I put a list of many people, HTK, Penrose, and Gabriel Veneziano, of course, and many other people. There's a very large literature where people have proposed a model to go through the big bang, the big crunch, and do a bounce in the space-time in order to be able to cross the singularity. So we have all this, part of this material in mind. And what we do here is that we don't look specifically at a model of modified gravity. We look exclusively at the Einstein equations. And we look for a framework which we hope to be flexible, to cover a lot, many different scenarios that people have proposed before, and do a systematic study of bouncing junctions at interfaces. And I should say first that all I will present here is in the regime of what is called quiescent cosmology, and I will return to that. That, if you like, in a shortly, you have an oscillating regime, a monotone regime, and what we treat here is a so-called monotone regime. So the main result I want to show you is a classification of bouncing laws near a singularity hypersurface. In a way, and the main conclusion that I would like to tell you about is that we discover that the scattering phenomena taking place at a singularity in a space-time, this phenomena can be somehow decomposed into universal laws of bouncing and model-dependent laws of bouncing. So this is maybe the main message that people did not realize in this context before, is that there are a lot of different laws that have been proposed, but some have a universal character and some do not. The theory has been applied to construct cyclic spacetimes, where you go through one bounce, and maybe later on there is a second bounce coming, and so on and so forth, possibly finitely many of them or infinitely many of them. This is a construction that we can make in, of course, not in a general situation, but by assuming T2 symmetry. So you have two killing fields in your spacetime. We have been able to analyze the collision of two gravitational waves and go beyond singularities. And this is an old problem started by Penrose many, many years ago. And what we contribute to here is to explain how we can go through the singularities by certain scattering laws that we put in a class of laws in some sense. So the way the talk is organized is that there is a section where I will give you some element of mathematical general relativity in this section 2. Then I will introduce the definition of scattering maps, cyclic spacetimes that we have defined, and then explain you this classification of maps that we have discovered. If I have time, I can show you some results for the collision problem of plane waves, and I have even a small movie that maybe I will show you in the end. So this is the background. What you want to do here is that you want to look at Lorentzian form manifold satisfying the Einstein equations. And you should only think of the Einstein equations as being a big system of partial differential equations connecting the geometry, the curvature of your spacetime to the matter content of your spacetime. In order to formulate the initial value problem, you need to prescribe a slice in the spacetime that you want to construct. And the slice is actually a Riemannian manifold with a metric, I denote it by G0, and another field, symmetric tensor fields that express the extrinsic curvature of the slice in the spacetime that you want to construct. Okay, so this is a way that the initial value problem has been formulated 50 years ago by Choquet-Bruat, for instance, and Lichnerovich at that time also. So you have a certain hypersurface in your spacetime that you want to construct. You put data on it, meaning metric and extrinsic curvature, matter field, of course, in my situation, and you want to evolve globally in time, or in a maximal sense in time. I mean, all the difficulty is to understand what is a notion of solution you want to work with, and in some sense, how far you can go in the evolution. The data cannot be arbitrary, because if you know the Gauss-Kodadzi, you think of the Gauss-Kodadzi equations, there are some constraints that the data G0, K0 should satisfy. And these are essentially nonlinear elliptic equations. In the vacuum case, there are a lot of results of nonlinear stability of solutions, beginning with Minkowski spacetime, and much more recently for Schwarzschild or Kerr spacetime. I'm not talking about that here. I'm interested here about the role of the matter and the situation where you go beyond this asymptotic symmetry. And I will begin with just one-page result. One result I have with my collaborator Yuma about the nonlinear stability of Klein-Gordon field. So you have now the effect of the matter taken into account, and you ask the same question of nonlinear stability I just mentioned. The second issue is whether you can construct solutions that asymptotically are very different from being spherically symmetric. Which is a case of Schwarzschild solution, or Minkowski even more. So you want to ask whether there are solutions where different directions will have different asymptotics, and this is a result I have here with another collaborator, Nuygen. And then I will move to the main topic, which is the evolution when you have singularity hypersurfaces. Right. So the way I see that is that you want to go beyond Minkowski, Schwarzschild, and allow the role, some effect of the matter, even the singularity hypersurfaces. Of course, this is an issue without the matter, but in a way, matter and asymptotic symmetry, beyond asymptotic symmetry. This is has been my main concern in the past years. So let me show some first result about self-gravitating massive matter field. So you just ask the following question. You put a Klein-Gordon field, and the equation is just written below here. So it's a wave equation with a Klein-Gordon term, with a certain mass term, non-vanishing. And when you do that, you actually no longer have the scaling invariance of your PDE. And so this does not interact very well with the Einstein equations, right? So you lose a certain scale invariance property, and this is a source of all the difficulty, all the mathematical difficulty behind, and maybe also all the interesting, rich, complex dynamics posed by massive matter field. And the type of question you ask is that if I put some matter, maybe not too much, a small perturbation of the vacuum, say, and I wait sufficiently long, do I reconverge to Minkowski space? And this is a question we answered positively in a way that allows decay conditions at infinity. So the topology will be R3. It's really taking Minkowski, slicing Minkowski, and I have a picture maybe to explain a little bit more what I'm doing here. But you should think of your space-time coming with a foliation. My foliation will be a little bit special, but first think of something that is asymptotically Euclidean. And the asymptotic in space is very important because it prescribes some of the physics. And I will show you in a minute on the next slide that I can construct initial data sets satisfying the Einstein constraints, where the asymptotic in space is very different in different directions. Okay, so it will be Euclidean in one direction, say Schwarzschild in another direction, and some kind of interpolation in between. I show you another picture in a minute. But at this level, I consider that this initial data set is given, and I assume that it's sufficiently close to Minkowski data in some sense that is expressed in weighted Sobolev spaces. And I can prove that there is a global solution of the Einstein Klein-Gordon system, coupled system. In the terminology of general relativity, is called globally hyperbolic Cauchy development, but it's a manifold. It has the same topology, just a trivial topology, and the metric has a number of properties. So you have a foliation by asymptotically flat hypersurfaces. Your space-time is future causally geodesically complete. So somehow you have constructed all the space-time in some sense. And you have also some asymptotic toward Minkowski, both in time-like and space-like directions. So this is one typical result you can prove. And I will just say a few words about the proof. The proof is done with a new technique that is called Euclidean hyperboloidal foliation method. And the name comes from the picture, or maybe the picture or vice versa, but there is a picture that shows you the foliation that we construct in our problem. Okay, and you can of course describe your space-time with any foliation you want, but since our problem is quite I told you about this coupling. At the end of the slide, I wrote coupled wave Klein-Gordon equations. This is what we study at the level of the analysis, and so you have to combine techniques that apply to wave equations and techniques that apply to Klein-Gordon equations. And the two, they don't go very well together, even though they are two, very classical equations. To combine techniques that may be known for each of them is delicate. I mean, it really requires significant changes. And the main reason is that the scaling field cannot be used to control the metric, and cannot be used, of course, to control the matter field also. So, okay, so this is very sketchy. You see the picture, and the picture shows you the foliation. And the foliation consists of 3 types of regions in space-time, where in the outside region of a certain cone, light cone region, you have an asymptotically Euclidean foliation. And inside the light cone, region, you have an asymptotically hyperboloidal foliation, and both of these foliations are very important, to capture properly the decay at time-like infinity and the decay at space-like infinity. Okay, so I would like to move on and now tell you about the constraints. So to apply this result of global evolution, I need to construct the initial data to say that I have enough initial data with as general as possible. And here there is a recent work by Carlotto and Schoen, where they ask some of these questions: localization at space-like infinity. So they construct solutions to the constraints, localized at space-like infinity. And you will understand in a minute what it means. And what I have done in connection with this idea was to relax their requirement at infinity in a way that I believe is as physically natural as what they were requiring. And this is what I do. So the result again is joint with Nguyen. We call it asymptotically localization problem, and it goes like this. You have a manifold, and you with one asymptotic end, and you look for solutions to the Einstein constraint equations, where you think of two disjoint angular regions, which I denote by C Euclidean and C Schwarzschild. You can take any other metrics that you know explicitly, but there are of course not many that are known explicitly. So the two typical situations will be that, Euclidean and Schwarzschild. And this is what I prove. I prove that there exists a solution to the constraints, which have the asymptotic 1 over r, meaning Euclidean, the trivial Euclidean metric plus 1 over r correction, where r is a distance in a chart that you define at infinity. So it's a way to state the asymptotic flatness of the metric. But then there are two more properties. One which is satisfied in the Euclidean angular region, and this is a picture that maybe with a picture will be more clear. So there is a small region which is on the towards the right side, asymptotically Schwarzschild. There is all the rest, or almost all the rest, where it is asymptotically Euclidean. And then you have two narrow regions, as small as you want, where the solution is 1 over r. Okay, so I guess I described maybe correctly the picture. And now let me return to the connection with the work of Carlotto and Schoen. In the work of Carlotto and Schoen, they essentially do the same, except that they get an information which is not 1 over r, but something with a slight slower decay, so less information, if you like, on the decay, on the behavior of your solution, but they get a better behavior in the Euclidean and Schwarzschild region, because they impose exactly Euclidean or exactly Schwarzschild. Okay, so you can view it as maybe a dual way to what they had constructed, but it has been fun to do that. So let me, I think I explain what I wanted to say here. And now let me move to really the main topic now, is to say you have all these matter fields and you want to allow singularities. So the main goal again that I have here is to classify junction conditions at singularity hypersurfaces. So as I mentioned before, there have been a lot of work on that. The regime that I will cover here is a regime identified by Belinsky, Kalatnikov, Lifshitz. So they work in the 70s on singularities of the Einstein spacetimes, and they observe that there are two regimes: oscillating, monotone, and the regime again that I want to focus on is a so-called quiescent regime, where a certain monotone behavior is satisfied. And you will see what it means by the statements that I will give you. So what we do here, we approach a singularity and we expect some quantity to blow up. So what we do a rescaling of these quantities in order to extract significant limits. The limits, based on what I explained before, are expected to be on the hypersurface manifold, I mean, on the hypersurface of singularities. The limits are expected to be what? To be the metric, the induced metric, some information about the intrinsic curvature, and some information about the matter field. The matter field satisfies the Klein-Gordon or wave equation, so it has typically 2 degrees of freedom, which are like phi and phi sub t, or a time derivative of phi, if you like, which are denoted by phi 0, phi 1. So you have these 4 quantities that you will produce by rescaling. I show that more clearly in a minute. And what we are going to do now, we would like to understand how we jump from the singularity data on one side of the interface, say in the past, to the singularity data in the future. And we will do that looking for a classification by working with general spacetime. So we are not making symmetry assumptions. We are not assuming a specific model of modified gravity, because this would somehow tie our hands. So we would like to classify all possible junctions. And you will see that we reach quite, I think, beautiful result in the end. All works have been done by assuming some symmetry. Otherwise, the techniques that are used in this field, if you don't assume symmetry, you don't know what to do, right? But our point of view is not to put symmetry assumptions, but to rely on the Einstein constraints, which I just discussed, right, for a good reason. And the discovery is, I repeat what I said earlier, we have universal scattering laws and we have model-dependent laws. So let's see what this is. So I need to go through number of notations, so you will accept hopefully that I show you some technical notation, but eventually there will be a formula and 2 slides with rather simple formulas for the junctions. So what you need is to have a Gaussian foliation. So this is my notation for the foliation, and to express the Einstein equation as a flow. And I know many people at Stony Brook have worked on that with Mike Anderson. And so I look at this flow, but I'm not asking any question about the global behavior of the flow. I'm looking at the local behavior near the singularity. So this is a picture that I have in mind. I have a singularity hypersurfaces in a black, it's a thick line. And I'm going so I have a foliation. I'm going to define something we call asymptotic, some asymptotic solution, some asymptotic expansion, which is a quantity with a star. And each of them, we will define certain limits, which we'll call like it's written here. Oh, okay, so this is a general goal. And to begin, let me say that you have an example of what the asymptotic behavior could be, which is given by the well-known Kastner profiles. So I wrote an expression of a metric parameterized by X will be a parameter on your singularity hypersurface. There will be no, just a parameter at this level of the description. And you define your metric with some exponents, P1, P2, P3, which has a so-called Kastner exponent. And the second fundamental form is given just to be diagonal over tau, right? So you see that you have exponential blow-up factor in the metric, and you have a blow-up of 1 over tau in the curvature. And the matter field blows up like log of tau. Okay, so I'm just saying that this is an ansatz that I will motivate, or maybe not in this lecture, but can be motivated and more importantly, can be justified as being a good expansion on the singularity. I guess I speak too fast because this is only an example. Okay, so the precise asymptotics will come in just a few seconds. But before I do that, let me explain a little bit more what I have in mind. So I have in mind a certain construction scheme where a gauge choice have been made in order to localize the singularity hypersurface at tau equals 0. And what you want to do, you want to put data on the singularity on each side, solve towards the past or towards the future, use the junction condition to cross the singularity surface, and derive. So of course you want to solve the Einstein equations coupled to matter, right? So the way this is done is to realize that the effect, and this is an idea going back to BKL, you have the idea that the space derivatives, if you like, in your formulation, I mean the space variation dependency will not be dominant, will be negligible at some scale. So you can deduce from the big Einstein matter system an ODE system, asymptotic ODE system, producing solutions that look like the one I put on the top of this screen. They are called velocity dominated in some sense, but this is an ansatz that you use in order to generate actual solutions of your PDE system. Okay, and so in the middle of all of that, the main issue for me is how you define the data on the singularity and how these data are restricted, and the jump, more importantly, how the jump is restricted by the Einstein constraints. Okay, and this is really exactly the question that we have addressed, and our main paper is on answering that, and I mean it took quite a lot of work to clarify that. Okay, so I see that the time is passing, but I think I'm doing more or less okay from what I want to tell you. So I need now a few definitions. So what do I mean by a singularity initial data set? So this will be a pair of two tensor metric G minus and a tensor K minus defined on a three manifold representing my hypersurface or any hypersurface in the foliation. You also have two scalar fields, phi 0, phi 1. And these should essentially satisfy the constraints, right? The Einstein constraints, except that I need to write them. I should write them only in some asymptotic sense. And this is what I did here. Okay, so I'm not, explaining in details why it's like that, but the slices would be assumed to be CMC, constant mean curvature. So the trace of capital K will be 1. After rescaling, so this is something you will see more clearly in the next, the second part of this slide. Maybe I can show you now. So there is a rescaling. So for instance, this K minus is used in order to define our asymptotic profile in this formula. K star of tau is -1 tau times K minus. Okay, so this is how you define a candidate, an ansatz for the expansive curvature. And there is something similar that you do, the Hamiltonian constraint, the momentum constraint, they put some restriction on your data, and you use this data in order to define an ansatz for the metric and for the matter field. So the matter field is like log of tau, and the metric is some exponential, so this is really an exponential matrix notation that is used. Now, the regime of interest I mentioned before is a so-called monotone regime. And monotone regime means that I'm going to have a contraction. So K minus this K will be positive. All eigenvalues will have a constant sign, which is a way to say that when you approach the singularity, you have a contraction in each direction. Okay, and then when you exit the singularity, you have an expansion in each direction. So this is a setup that we do here. We don't think that this is a very important, it's important in the sense that without this assumption, we cannot do any serious mathematics. But from a physical point of view or philosophical point of view, we believe that we discuss here, we present here ideas that go much beyond that. I need to continue with a couple of definitions. So you have now this foliation. What do I mean by a past to future singularity scattering map? So it's simply taking the singularity data from the past and associated singularity data to the future through a certain map. And this map is defined on the set, which I denoted by I of H, which is a set of singularity data that I just discussed. Okay, so of course this map cannot be just anything, and this is the precise goal, how you restrict this map. So we begin by saying it has to be diffeomorphism invariant, and it has to satisfy a certain locality property that when you do this junction, the junction should only depend on the restriction of the data for any open set. You want your data, you want to your map to be local. I mean, in this sense of having the restriction of the image to depend only on the restriction of your data for any open set. If you have this map, you can define a notion of cyclic spacetime depending on this map. So this is the idea that we have here, that we want to look at classes of spacetimes with a certain map. So the way you do it here is you say, okay, there is a set, the singularity locus, which I call L, and my metric and solution are smooth on each side of the singularity locus, away from the singularity locus, and the Einstein equations are satisfied. Then if you take a point on this locus, you require the existence of a foliation, and the foliation is such that you can now define by rescaling. So what you see in the blue and the red, so the red line is a junction condition that I will impose based on my scattering map, and the line before in blue is a definition of the data plus or minus on the singularity. How do I find them? I find them by using the ansatz, the assumption that the ansatz that I proposed before was correct, and I will justify that. Okay, so assuming that the ansatz is correct, this is exactly by this formula that you capture by rescaling the metric in a certain way, by rescaling easily the extrinsic curvature, or more, it's more complicated, you can see it's more involved to rescale the matter field and actually capture the phi 0, phi 1 limit associated with the matter field. Okay, but if you do that properly, you can propose this definition, and you see with the next theorem that this definition is not at all empty. So we have a local theory which says the following: if you give me an analytic 3 manifold H0 and a map, a scattering map, like I just defined, which is preserves the positivity of K, which we call quiescence preserving, and you understand why? Because the expansion, the ansatz I'm talking about, is justified only in this regime. So that's the regime of monotonicity we want to talk about. So I fix some singularity data on one side of the interface, and then I can construct locally a spacetime that satisfies all the conditions I have imposed earlier. And when the slice is compact, you can look at the volume, you can analyze the mean curvature, which blows up. You can look at the curvature and compute all these quantities and understand that you have really a singularity with shrinking volume, crashing singularity, curvature singularity. And the proof of that is based on what I explained before, a Fuchsian technique. You have an ansatz, you prove that this OD ansatz is actually a good PD it generates a good PD solution. And you glue the two pieces according to the scattering map. Okay, so this is the end of one step of this story, and now I move to the question of, so this is somehow very general, very, abstract, but there are two reasons for this setup and our definition to be useful. First, we are going to do this classification, and the classification will, allows us to handle these maps and understand what are all possible maps of interest. And the second motivation for the definition that I propose, that we propose here, is also that in the case of plane symmetry, we have a global construction that we do, and which is exactly done, in agreement with our definition of cyclic spacetime. So in plane symmetry, you give me a way to jump across singularity like I described here, and I can construct a global spacetime with phases of expansion, contraction, and so on. I will show figures in a few minutes. So the classification goes like that. The locality property has already been written, but now what we are going to do, what we impose is what we call ultra-local map, which is to say that we would like pointwise junction condition. Okay, and we believe that most of the junction conditions, if not all, proposed in the literature satisfy this condition, but it would be hard to actually prove. But maybe we have a proof that comes differently from the classification. Okay, so maybe it's a different story. But so at this level, the additional condition that we impose is that we would like this junction to be pointwise, ultra-local map. And this is the only assumption restriction that we will make. Now, all the rest, conformal map or rigidly conformal map, which are conditions between the metrics, singularity metric before and after the bounce, or monotonicity preserving, which is a property that says that the curvature doesn't change, or the curvature is changed by 2/3 the trivial tensor minus k minus. So we have certain rules that can be found and have been proposed in the literature that we can also analyze and consider, but it's not a restriction for us. This is just part of our classification. So we can say, okay, why not this or that or that or that? And for instance, to be idempotent, you apply the map and maybe you apply it twice, and you want just to go back to the same data, or to be invertible. There are also notions that are different if the interface is space-like, which is a case of the bounces that I'm discussing, or time-like, which is also a very interesting setup that we have analyzed. So all these properties may or may not be satisfied, and they just enter in a general classification that we can produce. And now I arrive at the classification finally. So there are two theorems. One theorem I give you in a little bit more details. So this is the result. You look at a map, a scattering map, and you impose that it is ultra-local, so pointwise, and that it is rigidly conformal. So you go from a metric on one side, G plus or G minus on one side, to the metric on the other side, G plus, by a conformal factor. Okay, but the conformal factor can depend on the rest of your data. So the only restriction here for this class, but the next theorem will give you the result. Maybe if I even show you the whole page, you see where I'm going. So there are only two classes of ultra-local space-like rigidly conformal singularity scattering maps, which are the ones I write here. So isotropic, non-isotropic. In the first one, what you do, so you arrive on the singularity, and what you do is that you somehow erase a lot of information that you had in the past, in a way, in the sense that the matter field, phi 0, just becomes a constant. There is some normalization, but it's not important. And phi 1 is also a constant, but it can be an arbitrary constant in this model. So you erase the information from the matter, Then you replace k plus by delta over 3, so just equal Kastner exponent, and then you do a conformal transformation of your metric before, and you do it according to conformal factors that depends on your data before the bounds, the matter content, and the determinant of k minus, right? So you use a little bit of the information from the past to define the future with this in this case. But you can also do a non-isotropic conformal bounds, which is given by some other formula. In this formula, mu c square is a constant, mu is a function. K, you can see that k plus is the trace-free part is now changed. You can see with a factor mu to some power, and the matter field also has a certain transformation. And there is a formula which is below to tell you what mu and capital F is. So what is really amazing here is that you only need a constant c. I mean, it's maybe mostly irrelevant, but you need a function, a single scalar function f, to define the bounds. Okay, so that's it. Just that is enough. So you don't need a complicated, theory. If you are in this setup, having ultra local jump and you assume rigidly conformal, you only have this possibility and this degree of freedom. Of course, you could say that rigidly conformal is maybe a big constraint. So in some sense, it is. And this is why we have a general classification where this assumption is not imposed, and the result is very similar. Okay, a little bit more complicated to write because the analog of lambda is now not a scalar; it's not conformally invariant, so it's not a scalar; it's a tensor. I mean, it's more complicated, but the philosophy is really the same, and more than that. I have another slide. So I guess this is really maybe the main slide with the next one that I wanted to show you. That is a reduction with very few parameters. And all of that comes because we have not assumed symmetry. We treat space-time without symmetry restriction to begin with. And we play with the constraints, with the Einstein constraints. So they impose, for some reason, they somehow impose a lot of what should be possible for the junction, or only that is possible. Okay, so in the last line you see lambda is a two tensor, capital phi is a canonical transformation. So there is a little bit more that I've hidden here, but I can show you a little bit more about this classification. Is that from the classification, we can actually extract three laws, which say, the first one says that the Kastner exponent have a certain scaling, written, in a very simple way. There is a constant that we call dissipation, gamma, and you jump from one side to the other side as far as the trace-free part of K is concerned, rescale by the volume factor, G to 1/2. So if you do that, this quantity is continuous modulo a certain gamma. Then there is a second law that tells you how the matter is transformed. And we found out that there is a structure of a map that is preserving the volume form in the phase space of, say, the data phi 0, phi 1, essentially, in this space. And this map, so it preserves the volume, and it depends only on a single parameter, which is a determinant of the trace-free part of the curvature. And there is a third law, which we have called directional metric scaling, that tells you how the metric jumps. Right, so in some sense, this slide is a way to present the general formula from the previous one. And again, the message here is that there are very few parameters that are needed in order to characterize all the dynamics. And so with this idea in mind, I guess I can now arrive to one of the last slides. Now, of course, you can say that we only did, you know, of course, a very small step of this the whole story. And what we would like to do now is to connect our framework with models that have been proposed by many people, and especially my collaborator Gabriele Veneziano has proposed a certain scenario for the Big Bang. So hopefully we will be able to connect what we have done with his earlier proposal. Of course, there are other models, and don't ask me questions about these models. This is something I want to learn, basically. But this is a philosophy that I have in mind, and it comes from me from work I have done over many years on fluids. So I've actually studied fluids before I was working on general relativity. And so the way we see these bounds, according to what I've already explained, is that we see it as a sharp interface. So we only want to look at the Einstein equations in the end. Of course, we need some information from small-scale physics, and this is a point. But what information do we need? This is the kind of question that I have treated for fluid or material dynamics also would be like this. If you do typically this Martensite austenite phase transition, you know, you have some interface and the physics will be different on both sides, or it could be a fluid in two different phases, a liquid, vapor. And so in this context, you need to take into account effect from viscosity, surface tension, heat conduction. But maybe you don't want to resolve, for instance, numerically, you don't want to resolve the small scale physics behind this. You only want to capture the physics at a certain distance. And this is done by typically what is called kinetic relations in the context of phase transitions in material science. So this is what I have in mind now. We have a flexible framework. We have somehow uncovered all possible classes of junction. We can classify them. They are meaningful geometrically and physically. They can be put in different classes: conformal, non-conformal, space-like, time-like. We have different things. Different matter models will also give rise to a different classification. So we have done that. And in the middle of that, you have certain universal laws that we have extracted. They constrain the bounces regardless of their origin from different microscopic corrections. And so they give already by themselves a certain guide to uncover the structure. But we have more than that, because we have really the full classification behind this. So this is really, I mean, a work in progress, and so do I have a few more minutes, just a couple of minutes that
well, you have like 12 more minutes or 14 more minutes, so it's 1 hour talk, but we started 5 minutes late.
Oh, okay. So thank you. So okay, so then I have time to tell you about plane wave collision. Okay, so how do we use these junctions for solving the problem of two plane waves? This is a problem that was posed by Penrose in the 70s. So maybe I have another slide where I mentioned this this work of Penrose of analyzing the properties of a plane wave in a space-time. So looking at the interaction of two plane waves is a very natural problem to look at, right? So you are an observer in the middle, and you have two waves that will hit you. And the way to formulate this problem mathematically is as a characteristic initial value problem, where we prescribe radiation data at past infinity. We can think of the waves to be of finite or infinite duration. And you think of your space-time in the easiest setup. Everything could be flat, and you have two gravitational waves that propagate. And again, you are an observer in the middle of that. The two waves will cross you, and you know what happens. And the first thing that you will observe is that there is a singularity hypersurface, and it's represented by this picture. So maybe you see, roughly speaking, what I mean. There is a wave, two waves, a Euclidean region, or I should have said, I guess, Minkowski region. And so the question is, I mean, the first point that was observed by Penrose is that there is a singularity. So what I put as a curve on in the gray region is actually a region in space-time. You have plane symmetry, so you should think of a point in this picture to be a two-plane or to be the torus, if you prefer. So the curvature is blowing up here. So classical definition of space-time should not allow you to go beyond that, but it would not be satisfactory physically if you cannot go beyond that, because you can think of an observer that will come, you know, and arrive, enter the picture at a later time. So if you think of it physically, and by discussing with Gabriele Veneziano, I realize that you really need to predict, to say something about the future. Otherwise, it's kind of incomplete physically. And so this is what we have done with this result, global plane wave collision problem. And we can show that when two such waves collide, we can go beyond the singularity, the first singularity observed by Penrose, by solving the characteristic initial value problem. And what we find is a space-time consisting of a concatenation of a family of anisotropic cosmological space-time domains, which we separate by, I have a picture and I said even a movie. So you have space-time domains separated by singularity hypersurfaces, time-like, null, or space-like. The Einstein equations are satisfied in each region of regularity. Across the singularities, we of course impose our junction condition, as I explained it. And we prove also that the curvature generically blows up, because there is always a possibility that your data will be special and the curvature will not blow up in some, but generically it does blow up. And what we see is a successive period of contraction and expansion with either finitely many cycles if the incoming waves have a finite duration, like I show in the previous slide, or infinitely many cycles if you continue to somehow feed the system with gravitational waves. And I want again to insist that the study without symmetry was essential in order to determine the relevant class of maps to be applied in plane symmetry. So even though the problem we have solved here is only in plane symmetry, to decide what kind of jump we could reasonably geometrically or physically do, we had to go through the whole program of analyzing solutions without symmetry in order to identify the correct class. Okay. And an example, of course, the simplest example, if you want something very concrete, will be what I wrote on the bottom line. So the metric will be just scaled with a certain constant, sorry, not a constant, will be scaled by this factor K, depending on your extrinsic curvature. And the matter field will just be shifted phi1 plus phi0 as written here. So this is the simplest, but it's part of a family of scattering laws that we cover by our theorem. And this family is just parameterized by one function, like or one or two parameters, like I described earlier. So I guess I arrived really to the end. So I have a few more pictures that represent the same thing differently. But this is really the same thing. And I show you a movie to finish, to conclude. And in the movie, you will see the area element of symmetry of the symmetry orbits, which is represented. And this is somehow, you know, the regions where, okay. So further reading, if you like, would be these papers. And normally I have the movie on, let me try if I can. Can you see this? Okay, can you see that?
Yes, looks good.
Okay, so this is 4 cases corresponding to 4 different initial data. And what you see is, so I guess the movie is just repeating itself, but you see the, you see a cross section of it, and so the different regions, and the color, I guess the color will represent the matter field, for instance, could represent the matter field. I mean, it's very simple. It's a plane wave case. But maybe to return to the conclusion is to say that what we want really to do is to investigate more about the physics. We have more mathematical analysis, global construction we want to do, and to continue this investigation beyond the plane symmetry. So, thank you very much for this.
Thank you for the talk. Any questions, comments?
So Philippe, you seem to be working with no cosmological constant, but in the real world there seems to be at least a positive one, and therefore most likely compact cross section. So, I mean, did you have any idea how you would move forward in this direction?
Yeah. I mean, as far as classification is concerned, there is no difference. It would have no effect on the classifications that we do here. It would have a negligible effect on you know, on the ansatz that we do on the singularity in this regime. Okay, it's a so-called Quiescent regime that we cover. So. So this is not, I mean, and also maybe I can also say again that it's a local analysis that we do, right? It's really a local analysis near the singularity. So in that sense, it doesn't have an effect on the classifications that we presented here. Does that answer your question, Marcus?
Yes. Also, a lot of the bouncing cosmologies, they exhibit violations of energy conditions. Is this relevant here?
Yeah, but this is a case of, you're right, but this is a case of all these models that I mentioned here. Okay, modify, etc., etc. So yeah, this is something that seems to be unavoidable at the junction. So again, I'm really not, I want to learn more about the physics behind this. But really what we have done is to look at the physics that was done, and there are a lot of work actually on in these different models. And we wanted to propose a mathematical framework that allows to say, to maybe connect the models together to see what is common, universal between the models. I mean, this was really the motivation here, not to say, you know, this model is good or this one is good, this one is good. I mean, this is just outside my expertise, at least, and that's not the game here. You know, the game is to say, okay, mathematically, can we do something clean and rigorous about that? And in particular, the construction of the plane. I mean, I find it very beautiful to be able to go beyond the singularity and to what we should be able to do. I mean, we are almost done, is to extend construction given by Penrose, Penrose. So Penrose, they have actually an explicit solution for the first region of you know, before the first singularity. So which was represented, if you like, by the triangular region here, studied by Penrose. So Penrose, they have an explicit formula where they put certain explicit data and they get an explicit solution inside, which is quite nice. And what we are able to do is we are able to extend their explicit solution to cover the whole space-time, extended space-time region with our junctions. So it's okay, it's fun, at least at some point. If I have a few more seconds, can I just show you a picture to tell you what I have in mind with the fluids? Because I'm quite excited with the idea of putting ideas that come from fluids with phase transition. So van der Waals fluid would be an example, and having structures that could be complicated like that. So this would be a situation where I see wave propagating, but the waves depend on certain small scale physics that is behind. So in this case, maybe I don't need to really tell you precisely what it is, but there are small parameters, capillarity, viscosity, some physical parameters that enter into the model. But if you change this parameter, you take them very small. If they are very small, you get shocks. This is what you see in the picture. But the value of these parameters relatively to each other is essential in order to decide which solution you actually see at the macroscopic level. And so the final picture, where you see all these curves, all this mass, represent solutions of the same initial value problem, of the same PDE, the same, you know, Einstein equations. It would be in our case, or the same fluid equations. And so you have to, you know, to accept that there are many solutions, and you have to find a way to understand how they are parameterized and accept that there is not a unique answer, a unique physical point of view, but there are many. But how many? Try to parameterize them. This is my issue, and I've done that for fluids, and I think we have done a significant step for Einstein in this case.
So I have a question.
Yes.
In this same line, I wanted you to compare your philosophy of your current result with your work in the past on fluids, per se, hydrodynamics. Can you make a comparison?
It's just much simpler for fluids in terms of so if you mean comparing the two classification. The classification for fluid is actually quite simple, There are no, you know, you don't have constraints on the singularity, hypersurface. This is really a different story. So when I say that there's an analogy in terms of the classification, it's very simple for fluids, and it's quite. I mean, it takes like 50 pages maybe of playing with the Einstein constraints when you want to play this game with the Einstein equations. So much.
The comparison with fluids, does it include anything about incompressible fluids?
No. What I have in mind here are compressible fluids producing shocks, and having typically phase transition phenomena. So really the typical example is what I put on this screen, and on the top you really see what I mean by having parameters with different scaling. So we have kappa, epsilon, and the ways that the two parameters are going to zero with a certain scaling will produce oscillations, no oscillations, a single limit or many different limits. But so even though the proof of the classification is very different for fluid, the basic answer is the same. That is, in the case of fluid, it's called the kinetic relation. So you have a jump, and you need to basically describe the speed of propagation of this wave, and it's something that is called in a context of material science. It's called a kinetic function, a kinetic relation. and this is the only information. So it's a curve. So that I guess I don't have, maybe I wrote it in a little bit more details, but so kinetic functions, scattering map, for me, that's the same story. And I have developed algorithms to compute these things by front tracking, shock capturing, etc. Okay, so I guess it's a different story.
In spirit, they're analogous, but specifically, they're quite different.
Yeah. The techniques are very different, but I think the philosophy is really the same. And I mean, I like that because this is really a way to pass ideas from one field to the other field. So
what you have two parameters here, and at least, and in the gravitational waves, what were the parameters?
Now here in this case there is a function, and the function is to associate. To describe a certain junction. I mean, there is more actually to this story because when you look at waves in a fluid, some of the waves will be compressive, and maybe that's too much, but the nature of the waves should also be discussed, and we have that in a paper that we'll post hopefully soon, discussing the nature of the discontinuities in terms of being compressive discontinuities or something which is called undercompressive, and there is this idea that because there is less compression, I mean the way that a shock in a fluid is formed because somehow you have information that I really would like to be able to have a blackboard and write picture, but there are ideas of compressibility behind that are important to understand the freedoms that you have in expressing the junctions.
Okay, thank you.
Okay, thank you.
Maybe I missed it, but what is the physical meaning of going beyond the singularity? So what happens with the universe when it collapses and then goes beyond this moment? So what is, how to interpret it?
I mean, the way you interpret it is to have in mind some of the scenario that are over here, you know. So this scenario physics, they tell you that you never go to zero, right? So you really have a scale, and so beyond the singularity is just for me a way to describe what I do at a sharp interface. A sharp interface description is really, you go beyond a certain singularity by, if it is space-like and you really cross this singularity. But the physics, the real physics behind, of course, has no singularity. But yet, the description where you allow a sharp interface model is very useful because it gives you the good picture when you are somehow far away from the macro picture is described in this way.
So these singularities would not correspond to something like black holes? Would?
Yeah, of course, it can be applied to any singularity. So
but would it mean that somehow these black holes appear and then disappear? So is it possible to make such an interpretation that black holes dissipate eventually? So,
yeah, so of course we can apply our law on the regime of a black hole singularity. Yeah, of course, yeah. Again, this is a local picture that we do. You know, we do a zoom, we look at one singularity, okay, and we tell everything that we can tell there. And we have this classification. Of course, you can now use that in a bigger picture, and we are not saying anything beyond that, of course.
But isn't the word singularity like a math word? You have a model, that model develops the singularity. It's a model of the actual phenomenon. The model develops the singularity, but the phenomenon goes on. I mean, it's not a philosophical problem. The singularity is in the model, and it might also be relevant to the phenomenon.
so but
I think Misha was asking, how can it make sense? If there's a singularity, what does it mean physically? But it's a math thing. It's in the, I'm saying it's the model you have has what we call a singularity. But, you know, in some statistical sense or something, in some other sense, the physics goes through the singularity. But you need another model to go through the singularity.
Yeah, I mean, this is exactly the point which is in case of fluid described by this. If you only give me in this case, if you only give me the fluid equations, you know, the one for tau t and ut, but no information about viscosity and capillarity, so uxx and 2xx. If I don't know these two terms, you don't give it to me, the model is incomplete.
Yeah.
But on the other hand, if you give me the full model with epsilon uxx and kappa blah blah blah, it's actually very hard to study this. I mean, it depends what kind of question you want to ask. But what I'm saying is that the effect of it sending epsilon kappa to 0 can be captured by interface conditions.
Mm-hmm.
But numerically, it's difficult to compute for epsilon and kappa very small. You need to refine. So it's interesting to some idea of what is a limiting model corresponding to that. So it's really a matter of point of view that you want. And my point of view is that I prefer the hyperbolic description, but I realize that it's incomplete. So I'm just looking for the missing information. And I'm telling you that this missing information can be classified, can be put in a very neat, elegant way in a single function or 2 or 3 functions. This is the main point.
Okay, then thank you again for the talk.
Thanks a lot. Thank you very much for this opportunity to talk and to meet you, even if it's to some distance. It was a great pleasure to talk to you.